All right, let's move on to the graph representation of an adjacency matrix, and we'll also spend some time at the end of this video comparing the two. So an adjacency matrix is one possible representation of a graph where you basically create an n by n matrix where n is the number of nodes or vertices, and you keep track of the edges by storing some value in the matrix that tells you whether or not there's an edge. So here's an example for an undirected graph. So you can see that red and blue are connected via an undirected edge, and so you can see that they're connected on both spots in the graph, one where the source and the destination are here and the source and the destination are here. If two nodes in an undirected graph for an adjacency matrix are not connected, like the cyan and the green node, you can see that those are labeled with zeros inside of the adjacency matrix. So here's an example of an undirected graph represented in a adjacency matrix, and it also has, no weights associated with it as well. Here's an example of a different type of graph that is directed and has weights associated with it. So let's go ahead and fill in the adjacency matrix for the graph that I have here, and let's use -1 to denote that there's no edge. There are no cyclic edges in this graph, so that's why right off the bat you can see that there is no edges on the diagonal of the matrix. Now we're just going to go node by node. So starting with A, we can see that there's two edges. There is one edge that goes to B, and there's one edge that goes to D. There are no other edges from A, so every other edge is going to be set to 0. Now let's go to B. B has three edges. It has one edge that goes to A with a weight of 80, has one edge that goes to C with a weight of 20, it has one edge that goes to D with a weight of 12, and then the rest are -1 because there is no edge. Then we will go to C. C has one edge going out from it, which goes to E with a weight of 29. The rest would be set to -1. Then we'll go to D. D has an edge going to C, so that's going to be a weight of 7. And then the rest are set to -1. Now we'll go to node E. Node E only goes to C. It only has an edge to C, which is 29. And then the rest are going to be -1. And then F is an island node that doesn't connect to anything. So A has 2, B has 3, C has 1, D has 1, E has 1, and F has none. So some of the things you might have noticed in this particular representation is that we used a different marker for no edge. We used -1 instead of 0, and that is because we have weighted edges here, so we have to choose something that wouldn't be a possible weight. Also can have cyclic edges. We just don't have any in this graph, and so they're all set to -1. So which of these variations cannot be supported with an adjacency matrix? So we just talked about cyclic edges, so those can be supported, right? They would be supported on the diagonal. In this example, there's a cyclic edge, and so you can see that there is that weight of 10 there. I've shown you both examples of using a directed or undirected graph and representing it with an adjacency matrix. It's slightly different, but you can see that they both work. We also know that weights can be present or absent. We can use zeros and ones, or we can use their weights themselves. And so the only thing that we have left here is that one thing that you cannot represent in an adjacency matrix is multiple edges from a source to a destination. So that's something that you could do in an adjacency list, but it's not something that you could do in an adjacency matrix. Let's talk about some other differences between adjacency matrix and list. Let's say that we have a graph with n vertices and m edges. What would be the space requirements for each? So for an adjacency matrix, we have n rows and n columns in order to fill out that matrix. So n is the number of nodes. So the space requirement is going to be n squared. For an adjacency list, we'll have a copy of each node in the main list to keep track of the source node, and then each of those will connect to all of its edges. So total space is going to be n plus m. So you'll need space for every node, but you'll also need an additional space for every edge. That edge could just be storing its node in weight, but it is on the order of n plus m. So those are different. So they have different space requirements for an adjacency matrix for an adjacency list. As far as time complexity, it really dramatically depends on how the implementation is set up. It might require traversal of the data structures or the abstractions in order to look up an edge. For example, if we wanted to know if there's an edge between Dallas-Fort Worth as the source and the destination is Ordway, we could go to Dallas-Fort Worth as the source and the destination is, what did I just say? O'Hare. Then we could see here that it's -1, so there's no edge. What the actual cost of that would depend on how the matrix is implemented and if you have any way to connect your nodes to the actual indices of the matrix. And you could do that. You could probably think of lots of ways to do that. And so it's possible that you could get lookup in O1 for the matrix. Same with the adjacency list. It really depends on the implementation, right? So like if we know that we've used a map, lookup to a particular node might be log n, might be O1, depending on if you use hashing or not. And then once you get to a particular source, then where are you at? Do you have a set? If you have a set, what's lookup in a set, right? So if it's a set, it might be log m. If it's a hash set, it might be O1. If it's a vector, it might be m, right? So it just depends. So lookup is really going to depend on what kind of abstraction you set up. And then remember that if you are using hashing, which you could imagine is potentially possible, it depends on your hash function. So if there are collisions with your hash function, then because it's bad, then it's also not going to be O1. So after talking about some of these differences, as you can imagine, most graphs are sparse and each vertex just has a few edges. So if you have a graph with 10,000 vertices and the average number of edges per vertex is 5, which representation should you use? So basically, if you have a sparse graph, what is the best representation? So definitely an adjacency list. An adjacency matrix would set up a whole set of memory that is going to be never used, and it would be kind of wasteful. Where an adjacency list with the O(n plus m) space complexity is going to be much more efficient for sparse matrices. But there might be some overhead in time for lookup, possibly, depending on how you set up either. All right, that is it for this video.